Welcome back to the fifth part of the assembly tutorial for Snake, the Easter special, even though it's now past Easter. And we're on the fifth part, and that's where we hopefully wrap up what we set out to do. Last time, if you remember, we finally made the snake grow. We placed the food on the table, and we made sure that the snake grows once we touch the food. We struggled a little bit with the coordinate buffer there at the end, but luckily we figured that out. Today we're going to make sure to find the hit detection and to make sure that the food doesn't spawn within the snake. That's pretty much the same function. We don't have nodes, the x86 just gave out, so at the end we might rely on some back and forth. We will see about that. For now, the first thing we're going to do is revisit the sleep function for a moment, because we need battery, and the sleep function that we used was a very good way to introduce the sleep. We have a busy loop, and we just told the CPU, here, go there, and just go in a loop, pretty much telling him to go brrr. That's very inefficient, and if you run the program, you will have noticed that the program is actually, or the terminal is signaling, hey, high efficiency or high energy usage, and that's because the CPU just goes full throttle, and that's not really what we want. A way better way on modern hardware is to do something, well, let's put it this way. Modern hardware has dedicated elements for that, right? There is an element which pretty much says we're going to schedule this for, let's say, 2 seconds. So we add 2 seconds to it, place it in a queue, and then the hardware is going to check every, I don't know what, microsecond, maybe nanosecond, is it now time? And once the time has arrived, that is going to be passed back to the CPU. And because that's designated hardware for that process, it's very efficient, and the CPU has time to do other processes in the meantime. So we're going to use a very old Linux syscall called select to accomplish that. It's pretty much a side effect, but it's good for our purpose, and you will notice immediately that it's way more energy efficient. So that's the first thing I want to do today. So let's go here. I'm going to take the sleep function, and I'm just going to copy it. Can I go down here, and then I comment our old sleep function out before we will retire it later. Oops, gv. No. Undo. We're going to use this. So now we have the sleep function and the select syscall. I'm going to remove our busy loop here. This is all retired now. Works with the select syscall, and as always, the write-up will be on the GitHub eventually, I promise. But I have it here. You just need a struct for time. Again, 8 bytes for second, 8 bytes for microseconds. That's the syscall number. That's what we're going to use. Nope, that's the x86. We're going to use 93. Same spiel, and it goes in x4. So let's take 93. Let's take 93. I'm going to place EQ sys select in 93. Oops, 93. We go here, and I'm going to move x16 gets sys select. So this is that. And then we saw here we need pretty much something in x4. So let's go down here, and we have to be careful on the arm64 with the stack alignment. So let us go where we already had time of day, random number, let's say here, I don't know, speed time adjustment, speed adjustment. I'm gonna change that name. I just don't know what the name I chose. Adjustment, it's gonna get space 0x10. I'm gonna copy that. I'm gonna go back here and we're gonna not move. We're gonna address page that. Address page x4 in there. And we're gonna add x4 speed adjustment at page off. So that is that. And then the other, because we're not really using the select syscall, we're more using it as the timeout is more side effect of it. So x0 is going to get a 0. x1 is going to get a 0, x2 is going to get a 0, and x3 is going to get, holy moly, a 0. Is that correct? 0, 1, 2, 3, 4 gets the address. Here's the syscall, and we need our supervised call. This is 0x80. Let's check if we are still compiling. Maybe we should have checked. Oh, we commented out the sleep function. That's fine. So our sleep function is not working. That's because we need to actually say the second's going to be quad 0, and the microseconds we're going to set them to, I don't know, 8,000, I think. Oh, and there we have something. 8,000 seems to be a little sluggish. Let's take an A here. And there we have a movement. And you will notice that this is way more energy efficient. And here we have just a microseconds number and using the select syscall to time out the system. So here we are. We can eat our food. We are growing. The light is now slowly disappearing. So now you see we don't have food, so most likely the food appeared in the snake, and that means we didn't eat it, but it's also not displayed anymore because we just overrode it with our snake. So now you can go for a hunting here and see if you will find it. If not, it doesn't matter. Let's just restart it for the moment. We cannot kill ourselves. So now the task is obviously to go ahead and make a hit detection. So the idea is to write a function is element in snake segment, or is element in segment of snake. I think that's what I named it. So without further ado, let's do that, because we have now two things. We have one time the food and one time the head. For the head, obviously the head is in the head, so we only have to check for the head that it's not in the tail to head -1. And for the food, we have to check that it's not from tail to head. So we want to have that, that function be usable for both cases. Put food on the table. So maybe we go, what is here? Print playing field. I guess this is as good as any. So is element in segment of snake. And is element of segment of snake. Then we're going to move stack pointer fplr. No matter what happens today, I didn't forget the bang here. Move sp stack pointer into the frame pointer and stake pointer into the frame pointer, ldp fplr sp, and readjust the stack. Good. So let's write down what we actually want for the function. So in xnull, x0, xnull, who cares? We get the address of the element to check, element to check. In x1 we get the starting address, and starting address, think of tail, and in x2 you're going to get the end address, and that think of head or head minus 1. So first of all, most likely we need our elements. So we're going to subtract from the stack pointer 16. Okay, 1 second. All right. We're going to subtract 16 from the stack pointer. And now we're going to store. Let me think about this 1 second. The x0 variable will have the, let's think about it, the head will have the address of the coordinate buffer where the head is. So we would get that address, would retrieve the x and the y coordinate and then compare it to the elements which we loop over. So is x0 actually changing? I'm not sure. So we're going to store x0 on the frame pointer. fp is 8. And then I think the end address, we're going to store x0 and x2. The reason being that the x1, the starting address, think the tail, that's the one we're going to loop over, and because we have to add 2 to it all the time, we have to take the modulo function, so that value will change, but it will pass through the modulo function, but we have control over it, while x0 and x2 are lost the moment we call the modulo function. I think that's the reason. So we have that. So in x0 is our value. And now we have, of course, no idea what we used. So let's load 0, 1, 2, x3, x0, 0. And in x4, x0, 1. So this should be, think x and y head. And now move or loop through segment loop, call it segment loop. And I think I had an off by 1 thing here. So let's do this anyway. We compare immediately if the end address x1 is the same as x2. Compare x1 to x2 and branch when they are equal and segment loop. We are here. So that is that. Compare. We have this end segment loop. We need to loop through it eventually. So we're gonna branch to segment loop. But now we need our segment coordinates. We have 3, 4, so it's going to be 5 and 6, I assume. That's going to be in x1. So we're going to move byte x5, x1, 0, and in 6 is going to get x1, 1. So this should be x and y of the segment piece. Let's write this down for x of segment piece, and this should be y of segment piece. Piece. Well, it's not piece. Like free, give piece a chance. So piece, this looks okay. So we have 5 and 6. We have in 3 and 4 our head address. This is not going to change unless we override it. We have to be mindful of that. But for now, we're going to compare x3 with x5. If they are not equal, we're going to go the next segment. Get our label here. If the x coordinates are the same, we're going to compare the y coordinates. This should be now x2 and x6. And then branch not equal next segment. Right, so and here's what's going to happen if the head coincides with one of the segments. Next segment is going to be at x1. We add 2 to it. So let's check that x1 is the right one. x1 is the starting address. We're going to go through that. And now we have to modulo it. So modulo by what? Modulo range. That's going to be modulo range.
They're not, but unfortunately it's pretty close, you know? And I'm applying for jobs. We'll see if something works out.
So let us check what modulo range is. I think that has x0 the value. So the value is in x0, then we have the lower bound and the upper bound in x1 and x2. So let's go back somewhere here. So actually we want this in x0, but that's okay. We can just do that here. Then the lower bound should be the address of the coordinate buffer. It's the same thing we did last time, and the upper bound is the head. And here we have to do address page. Can we do that outside of the loop? x10 coordinates at page, and then at x10 x11 coordinates at page off, and in x10, oops, that's idiotic, it's 10, and now we're going to override x10 with the head at page off, and we actually want the coordinates as lower bound, so in x1, and this should be in x2. So if I'm not mistaken, which I probably am, this is modulo range of the function, and then x0 will be the value. So we're going to move back x0, x1 into x0. Exactly not this way around. So now we should have the modulo new head pointer. We are getting the new coordinates here. The question is, do we destroy x0? And the answer is obviously yes. So we're going to do, I'm not sure if this is the best way. We're going to place this in the loop, and then we can LDR x0 here. So we're going to get back LDR x0 frame pointer from the 8 offset. I'm going to comment this out. Pretty sure that's useless. Oh, whoa, I should have done that earlier. Move byte. You're right. Move byte is nonsense. That's just move, and that's a W. Move W x1 x0, and that's also not correct because that's a store byte. str byte store load, and that's actually a thing. This is definitely a store. This x0 is also a load, but x3 is an load byte. And do we have this here as well? No. Okay. Load byte right W. We have our W's here. There's a comma missing. Where is it? Here. Same spiel. And modulo range. That's branch label modulo range. Coordinates. Coordinates. But we want coordinates. Diantes, there. Coordinates. All right. We are compiling, but we are not calling the function. So, are we doing what we are setting out to do? Nobody knows. However, let's keep on moving. The next function that we need is using this function. So what we're going to do is check vital status. And check vital status, and let's go. stp fplr sp -16 stack pointer. What am I doing? Move the frame pointer in the stack pointer right about here. I hear music, I get terrified. Frame pointer goes in the stack pointer. Is this correct? Yes. ldp fplr sp16, and we're going to return. So we have the vital status. Now this is something we're going to do. Do not take my chocolate. So we're gonna do, we need a flag. Is the snake alive or is it dead? So we have something, food is served or something. It's like, so we're gonna check is alive. It gets another byte, and at the beginning it's true. It's alive. So let's go in our game loop, or not, a game loop, and I'm gonna do this for now. For now, we're gonna do this with an address page here. Address page x0 is alive at page at x0 x0 is page off. Again, it wants a comma. And then we're going to load in x1 the actual value. And that's not true. We need to... I'm getting harassed. We need the byte value in W1. And then we're going to compare it. Compare W1 with is alive true with, I don't know what I want, 0, if it's 0, branch equal end, branch equal end. The game loop, do we have that already here? We do not. So we have end game loop. So as of now, whoa. Always chill. Address page, this is also, why is there a comma? So this is working, so the snake should now, it should still be working. However, if we go to is alive and it is doing what it's supposed to do, and replace here 0, and now the program just exits because the snake, the program starts, the snake is dead, the program exits. So that's good. So we're this far, and now that we have done that, we can check vital status by how do we do that? We need the head, we need to have the address of the head, we need to have the address of one element before the head, we need to have the tail address, and then we're gonna give this to the segment function, and then we will know if it worked. However, while I was talking, I remembered that we didn't handle the return value. So whatever this is doing right now, hopefully it's checking the head coordinates with every element and then returns. But here, if it's the case, in other words, if x and y are the same, we're right here, then we're going to move a 1 into x0, and we're going to jump, or branch better, here to the end. Right about here. Right, so we're going to pretty much say it's true. Is there an element in the segment of the snake? Is this element in any segment of the snake? Yes. And if it's not the case, in other words, if we end the loop here, we're going to move 0 in x0. So if we loop through the whole function and didn't find that any segment coincides with the head or later with the foot, then we're going to place a 0 in there, and that's our return value. That's the idea. So let's go back to check vital status. So now we have to pass this to our function. So we need obviously some address page 10, not 10. In x10 we're going to load snake, add page. We're going to add in the element we want to check is the head. However, the first thing we want, let's take the head page off. We want to have to subtract 2 from the head and then do a modulo function, right? So let's get right into it, because we have the head and we only want to loop to one element before the head. This is the address of the head, so we want to LDR x1. This should be now the address of the coordinate buffer, so we're going to subtract x1, 2. And to call the modulo range function, we need that in x0. So let's do that. And we need in x1 the coordinate buffer. So can we do that? Let's do that here in x0, and then let's try to get here in x1 directly the coordinates at page off. So they should be now here. And in x2 we need the end, which should be the tail, the head. All right, so let's use that. I'm trying to be too clever for my own good here right now, I think. Modulo function, that's what we're going to call, and in x0 should now be the element of the head modulo everything. x10 is definitely not going to be used in the modulo function. x1 yes, x2 as well. So we need x0 in x0, that's fine, but we need in x1 the tail. Oh, this is completely wrong here, ain't it? That's need on x10. So we need that, and now we have add x1 whatever. We want in x1 the tail, and in x2 we want x0. The element to check is the head. So we want, so here we have we took the head pointer, we subtracted 2 from the coordinates. So now we have one element before the head. That's the element to which we loop, and and that's in the function, in the whatever we call it, is element in segment of snake. That's x2. So that's why I place here the x0 in x2, and it's not adding, it's just moving. In x1 is the tail, but that's the address, so we need to LDR x1 x1. So that should be the address of the coordinate buffer. And now we just need the head. So let's take the head in x0 in x0, and also place this here, right about here. Address page. It's not address pages. Oh, the address page. What was the other modulo function? Ah! You saw. Right about here. Address page. It's not address pages. Oh, the address page. What was the other modulo function? Ah! You saw. You scare me now. Did you steal? Did you steal? Where are you? Harassed by a squirrel. Okay, branch label modulo function. That's what we actually want to do. What are you doing? That's a computer. That's not for you. Come here. It's jumping. I'm gonna place this right about here, huh? How about that? If you want it, you have to go there. It's on. Yeah. Go out of my bag. Okay. What do you? This is not for you. I can't believe this. This is here. Understand? More problems. Just because of you are annoying. Here you have a little bit. I give you a little bit. Here, come here. Come here. Remember, come here. Come here. And go. Go from my computer. Now this is done. Are we recording now? You're a little disturbing little thing. Okay. I don't know where we were, but we were here. Okay, we have, sorry for that. We have something, but we are not using any of this, so we don't get our segfault yet. Let's get our segfault. We coded it, we earned it. Where is it? So we grow the snake, branch label, check vital status. Nothing happens. I have a thing. Store stack pointer FPLRSP. That is complete. That's not even the bang. This is complete out wrong. Comma also. You get a comma. You want a comma. You get a comma. Here we are, and we are not crashing. Like, that's already surprising. But we are not doing the heavy work yet, so wherever we are, whatever we do, here we set everything up. So branch label. So now the squirrel ruined my Easter surprise, so I'm gonna get a little bit of Easter bunny here. Also good after recording for 2 hours. Is element in segment of snake. That's the real issue now, and now we're crashing. Good. But now I don't trust myself anymore in anything. FPLR, move stack pointer into frame pointer, yes. And segment loop. Are we even x1 gets, is x1 the counter? Is x2 stored? We should store, we're gonna load x2 here because I'm very, very confident that x2 gets overwritten in the mod function. So let's do that. Still not good enough. LDR x2 FP. We have x2 back. x1 should be here. And then branch segment loop. We are adding 2 to x1, putting it in x0. We have x1 the coordinate. That's the address. What address is that? We need to do this, what we just did, right? x1, x1, and the same spiel here. It's always confusing. So let's do that. Segmentation fault. We can live with a segmentation fault. Store register read x1. That's just gibberish. And that's, where is that? Right here. x1. So we are destroying x1, obviously. We add 2 to x1. We have the lower bound of the coordinate buffer. We have the upper range as head. Yeah, this is the head pointer. This is the... Oh, wait a second. This is not a pointer. Let me check that here as well. This is not the pointer. That's the real address. Tail and head here, that's correct. Object dump minus the snake. I'm not in the mood for anything else right now, so let's just check the vital status. lldb snake. Break set minus address right about here. Am I recording? When did the whole squirrel thing? Okay, we are recording. It's a little dark, but it's fine. So here we are. Check the vital status. I don't know what register. X10 is CLS. And now it's register read X1. It's the snake. Why is it the snake? Oh, but snake and coordinates are the same. That's fine. Step. Register read X2. That's the head. Register read X1 is the snake. Okay, so let's check that. Now we have snake plus 8. That looks correct. Now we subtract 2. That's also correct. Now we're going to branch into the modulo function. That's not correct. Okay, 1 second. Where are we? Check vital status. We're right about here. And check vital status. The modulo function. Here's where it went off the rails. Why are we calling the modulo function? We want modulo range. Modulo range. Right? modulo range. And is everything set up for the modulo range? One has coordinates. That's correct. Head is not correct. Now here is the head pointer. We are subtracting this. We need x0, we need the head pointer minus 1, but we need the actual head coordinate in x2. So we need to load LDR x2 x2. Am I right or am I wrong? Nobody knows except the debugger. Oh, something's happening. Nothing good, but something is happening. What is this? So, check vital status. We're going to do this right here. Gonna run it. Register read x1 is the snake. Register read x2 is the head address. Register read x0 is snake plus 8. That's correct. Register read x0, this is snake plus 6. This is the end of the loop of the thing. That's what we want to have in x0. x2, snake plus 8, this is not what we want. Here we want to have, for the modulo range function, in x2, we really want to have the address of head. So this is not correct. And in x1, we want to have the coordinates. Register read, that's snake. That's correct. Did we not write? Hello? So still not correct. Check vital status. We go here. Well, I'm going to go to the mod function right about here. We're going to check x0, snake plus 8, that's correct. x1 is snake, that's correct. And register read x2, head, that is also correct. Yes, all of this seems correct. Register read x0 is snake plus 6, so we're going to go next. And it's still snake plus 6. Okay. x2, snake plus 6. Now we're going to add register read x10. This is CLS step. Register read x1. We have the tail address. We have the tail. Register read x0. x1 should have snake plus 2. That's the starting point from where we want to loop. Register read x2, snake plus 6, and register read x0. That should be snake plus 8. Step, snake plus 8. Okay, we are good here. And now we're going to branch. Okay, our problem is somewhere here. Register read, wherever we are, whatever we do, x0. Snil snake plus 8, that's the head. Register read x1, snake plus 2, and that's snake plus 6. So this is good. We are now from the tail to just before the head. That's the wrong place, but that's okay. Now we have, okay, register read x0, that's the snake plus 8, that's the head. So we have it here. Register read w3, that's the 19, that looks good. Register read vw4 is the 7, that looks also good. That's the y coordinate of the head. Store. Why are we storing? What are we storing there? What why? What? Store of segment piece LDRB. LDRB. So this is complete nonsense. So let's do this. When we have something moving. So does it work? That's the question. Let's assume it doesn't, or let's assume it does, but we don't use the result yet, right? So let's do that. Let's assume it works, and if it doesn't, we check that. So check vital status. We check is the element in the segment of the snake. And now we're going to compare x0 with the value 0. So if it's false, is the head in the snake? No, it's not. That means branch equal to end check vital status. Otherwise, we move. We need is alive address, and this is, do we still have x10 here? Nobody knows, but we're going to take a gamble and say x1, x10 is alive at page off, and then we're going to move in x0 a 0, and we're going to store byte w0 in x10. No, in x1. And then we're gonna branch to the end, but we don't need to because we're already at the end. So that's interesting, but we are not here to play, so let's make this a little longer. And nothing. We are not, so this can never, let's do that one real fast. This can never happen in the game because, is this even correct? Because in the game we are just driving by. 1 second, because in the game we would be dead by at this point, right? So here, that's all interesting and fun, but that can never happen. So check vital status. Let me check. Move a 0 is alive. True is alive. False. We store this in is alive. So let me go object dump minus the snake is alive. What? Where are we? Why is this not here? Is alive. Grow snake, control snake, we had on end direction. Move snake, put food on the table, check vital status. End check branch equal. We're gonna go here. lldb snake, break set minus a this. Ask him twice. And we're gonna go here. Y. Now run it. Okay. Now you're checking that. Why are you checking this now? Register read x0. Check vital status. Okay, we check this here. We are now checking this here. I would love to have the breakpoint here. Breakpoint disabled, breakpoint set -r here. Oh, break, not BT. Okay. This doesn't work. Oops. Let's do that again. No. So we need two things. We need a slower snake, because I am not in the mood for this. Well, let's have a slower snake. Still pretty fast. Oh, way too fast. Oh, this doesn't work here. So let's do this. Are we still recording? Still recording, yeah. Freaking out. So this is snow, okay. Good. This is this. Now check vital status. Is element in segment of snake. Object dump minus the snake. Where are we? Why are we? What the hell are we doing? Is element in segment of snake right about here. Break lldb first. Break set minus address here. Okay. Breakpoint disable. Okay, how do we do this? Oh no, this is still too fast. Okay, we want to go here. We're gonna go. Holy moly. Okay, breakpoint enable. Okay, continue. So now, at least 5, 6, register read W2, W3, W2 is already weird, register read, let's go here, it should be, oh it's 3, 4, 5 and 6, so register read W4, this is 9, 3 is 20, sounds reasonable, 5 is 20, sound that, I don't know, yes, no, not sure, 6 is 8, 10. Register. This is the, oh. Yeah. So 20, 9 and 10. Okay, yeah, that's the y coordinate. We are at 9 and 10. That makes sense. Do I see, what is this nonsense? Do we still see the here? But why it's both 20, I'm not sure. So, okay, but we are comparing them. Next segment, not equal add to register read x0 snake plus 96. Actually, I have no idea if that's snake plus 96. We moved in the coordinate buffer. Okay. Register read x2 snake plus 20. How big is our buffer? It's 100. Something seems off here, right? Register read x0, 96. 1 is a snake and 2 is plus 20. Did we confuse the registers here? 96. Next. And now register read. Oh, they kicked us out. Is element in segment of snake. Let me check this here. We have x1 carries the element. x2 is the end address. x1 is the element that carries the thing. We're gonna add 2 to that and keep it in x0. Address page x1 has the coordinates and x2 has the head, and that's also correct. But this is not correct because the head we use as the pointer. Well, we could have died. It could have been so easy. It's also a little weird. So So what's the issue right now? So we have the modulo range. Where is our vital status? So the question is...
Is there another one? Is there another one?
Snake. Check.
Right down there? All righty.
Check.
You sure I can't just go here real quick? All right, all right. All right, all right, all right.
No, breakpoint disable. Continue. I want a longer snake. I want a longer snake. And I want to make this also longer. Oh, it doesn't matter for now. Well, 24 is close. Let's make this 250. No, lldb snake break. So let's check it here. Breakpoint disable, continue. No. Okay, again. No. In this direction, I'm gonna go here and now breakpoint enable, continue. So, register read x0. Register read x0. It's snake plus 314. We are at 500. Register read x1 is snake. Register read x2 is head. And the coordinates here, this is all from 83 over 84 to 85. That sounds reasonable. We're at snake plus 314. We're gonna next that. We're gonna register read x0. That's still fine. Why are we moving x0 and x2? Where are we? Register read x2 is 1. Step register read x2 is now this. I'm not quite sure. Oh, we're here. Okay. Register read x0, that's snake plus 314, that's fine. Register read x1, that's snake plus 270, and that's below, and register read x2 is above. That's the range. Does that make sense? Yes, 14, 16, that's one element before the head. Well, it makes sense a little bit. So let's check our values. Register read W3, A1, and 5, 1D. And 4 is 9, and 6 is also 9. 4 and 6 is 9. Why are they x1? What is this? This is the y coordinate. And we were 1 apart. Right? I'm not quite sure. Okay, let's keep going for the moment. Oh, I wasn't there yet. So 5 is here and 6 is A. And okay, we're comparing 6 and 2. W2 is register read x2. That's definitely wrong. What happened here? Segment. Two and 6. And that's 3 and 5 and 4 and 6. We are dead. Okay. Hail Mary. What? Okay, let's test it again. And we die. Okay. That seems to work. So now I think I'm pretty confident. We are off by 1 here. And we should do this check here at the end. So this is this. Because so in other words, the element before the head is not checked. Because once we hit that element, we don't see if that's the coordinate. We want to go over the loop, but we don't want to check the head, but we still want to check the element before the head. So let's test that. Okay, let's test it with exactly, I think 13 is here the magic number. No, I think 13 still works. Let's CMake. No, not CMake. Let's check this. This still works. No, 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 don't eat it. This still works. Now we're going to eat this. No, you're going to eat it, and now we are dead. So that's good. What time is it? Game time. Boom. Now, okay. So now we know that we checked the vital status, and now we need the same function for the food. So put food on the table. Where is it? It's right here. So we check the food. We are loading whatever we do here. We get the variable and we compare it with the 1. And if it's true, if food is served, we bail out of the function. And then here we start generating the food. So now this is going to be a loop. We're going to create the numbers, then we're going to check if any of the food element that we randomly generated is within the snake, and if it is, we just jump back and cook again. So we're going to call this here keep cooking, because then we can easily branch right about here to keep cooking. X coordinate. So here we store it. Let me see what we actually, here we place it on the field. Here we get, I don't know what. Here we get the, I think here we store the X coordinate or the Y coordinate, one of them, I guess X, and here we score Y. So if we're not completely idiotic, then this is X and this is Y. So this is stored here. And W4 is X, I think. So here we place it on the table. So that's where we want to have, we want to call our isItInSegment function. So we need in x0 what? We need the food. We have it here in x3 as far as I can see. So we're going to move x3 and x0. In x1, we need the coordinate buffer. Do we have this here? Food is served, no. We need the coordinate buffer. Do we have to get it anew? So maybe we just do that. Address page, x1, screen buffer, coordinates is at the very top. So we're gonna get this address x1, snake or coordinates, this add page, and then add x1 coordinates add page off. That's that, and then we need the tail. So let's use that in x2. That's gonna be changed till at the head. However, that's the address of the head. What we want here is load x2, x2. So we get coordinate buffer. What am I talking about? Why am I modular ranging here? We want to call food, and we want to call head to tail simply. We don't need, we need head, we need tail. That's all we need. So let's take snake. Then let's get the tail. And let's get the tail.
Extra is the next one that's open in 61st Street. All right?
Snae.
Best way to walk down there?
So we have the x1 has the snake. x2 has now the tail, and x1 has the head. Actually, we want this the exact opposite around, right? Or do we? Yes, we want to have x1 the tail, x2 the head, and those are the addresses of what? The addresses, we don't want that at all. LDR x2, x2. Now we have the coordinate buffer, and now we have here x1, x1 the tail. So what am I doing? x2, x1. So now we should have the coordinate buffer the tail, we should have the coordinate buffer, the head, and in x0 we have a 1. Why do we have a 1? In x0 we want the food. So in x0 we want what was previously, am I in the right function? Okay. I don't know what that is. We leave it there. Oh, I hope I didn't mess this up here. So let's go here. I think I want it to be here. Bus error. I messed it up. Object dump minus the snake. Put food on the table. What's the time here? I'm still talking. Break, set. It's still recording. A lldb snake. Break set minus address. So we here. Oh, we have food is served, huh? Oh no, it's not. Okay, we have a random number. I don't know where I am. We're in generate pseudo. We keep cooking. Okay. We're gonna try to jump over that. We didn't. Keep cooking. Okay. Register read W, register read W6, that's our number. 2A, that seems big, could be an X coordinate. Store byte, what is register read W6? 2A. Bad access, oh, register read X1. Yeah, we messed something up. Sorry, I messed it up. Don't know where the X1, W6X1. W6X1, I would assume it's here. X1, so X1 is screen buffer. So I assume that here is something missing, like address page x2 screen buffer. No, it doesn't even add page off, of course not. So we have this, still bus error. X1 still here. Screen buffer add x0 to x1. What is x0? X0 should be the screen buffer right now. X0 and x1 is this thing that we calculate here. This is x1, x0. This should be a y coordinate. Is this stuff here? I don't know. I'm just copying this down here for a moment. So we get this back. 8, x3, and then x, this should be x in x4, and y should be in x0. And that's another topic there. So lldb lldb ldr x3. Why is it segmentation fault? Well, we are upgraded from a bus error to a segmentation fault. And it smells like somebody missed a proper. Register read x3. That's a 5. Why though? I thought we store here the, that's the x and the y coordinate. I thought we have, okay, we have the x and the y coordinates directly, so that's also fine. Then let's load them. Is this x or is this y? One of them is y. So assume that's x and this is y. Now we should die, right? Yeah. Okay. We are doing something. Oh, we are still slow. X and y. Symbol food. Screen buffer, symbol food. Food is served. Okay, here we get the x and y coordinates back. Where do we store them? LDR, where is our, this is our, here we are storing them, and here we have the food. So here, that's what we were working on. That's our snake, our head and our tail, and now we want to check if that's in the segment. Let's assume we set everything up. So we would branch label is element in segment of snake. Well, not crashing. Slow as hell, but that's because I set it to FFFF. Okay, so now, but we should definitely, okay, we are, if it's true, compare x0 with 1, that's true, branch equal to keep cooking, right? That's the gist. So let's make it faster again. Maybe like this. I think it can be even faster than that. Now let's check for a moment if we just get this proven by an element spawning within the snake. Yeah, well, I have to play better, otherwise, well, it's not happening, but it can just be coincidence right now. It's not oh! This again! You thief. You thief. Ah, it has some chocolate there. So let's, let me check the camera. Nobody's here anymore. So let's check. Let's just run through it. Object dump minus d snack. Snack. It's here. I have to come and get it. What if it's here? Now, are you willing to do whatever it takes to get your chocolate? No, you're like, nah, he too creepy. Okay. Put food on the table. Is this where we are? Break set minus a. Is lldb. Snake break set minus the address here. Okay, food's on the table. Step. Food is served. Is it served? Register read W0. No. So we're gonna generate a pseudo random number. Why are we in here? And put food on the table. Game loop. Why are we here? Oh, now it's served. Wait. Breakpoint disable. Continue. How do I get here? Breakpoint enable. Continue. 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 Huh. Step. And register read W0. Food is not served, we just ate it. So we have to generate a random number. Can I please go here? Set minus address. Continue. I'm gonna do this right now here as well. Address here. We're gonna continue. Register read x0. Oh no, this is just a value. That's all fine. Nope. Gonna go here. Break set minus address here. Continue. How many? What are we doing here? Break set minus address here. Continue. Where are we here? All right. So register read x0. This should be food. Good. So let's check. We have 2a and 0b generated. Register read x1. This is tail. Oh, we're gonna do one more. Register read x1. This is snake plus 3 whatever. x2 is snake plus 358. So there. What's the difference here? I don't know. I don't even know how long the snake is, so can't tell. So we're going here. We're going in the loop. Register read x3 has 2a. What was the food? 2a, that's correct. Register read x5 is 18. I'm not sure if that's possible to get from 2a to 18. Register read x4 and register read x6. 1 and b, that's over. So we're gonna continue and it just appears down there. But we should be fine here. It's just like, do we go with trust me bro? I think we're gonna go with trust me bro. I'm gonna play. What am I doing? I'm like, I need a coffee and sleep. Okay, in that order. So let's see if it generates somewhere a piece that it should happen fairly frequently. But of course now I can die, so. Control is good. We need to change the escape key. That's one thing we 100% need to do now. And if we do the other stuff, I'm not. So, I mean, it doesn't appear to happen. We have we know we have the food coordinates, but do we have the tail and did I pass the right coordinates there, the right addresses? There's a point of failure. But at the moment it looks good. I'm gonna play here. Well, if I die, the moment I die, we're going to change the escape key, because I think we're fine here. All we do is use the same function that's working for the death, for the hit detection. No, oh, and I'm dead. Okay. So, one last thing. Well, is it one last thing? We don't know. One thing that we want to do is we're going to go to control snake. And what we're doing here is, if you remember, we do the syscall read for 1 byte, and we get the escape key that has escape and 40 something. Sys read, we're doing this here. And then we are loading. We are checking the value, and if it's an escape control, if it's not a control sequence, then we're going to escape. We're going to bail. We're just going to keep on moving. And here, then we check if it's one of the arrow keys. Now we want to check if it is escape itself, and if it's escape itself, we want to quit the program. At the moment, I just run the program. I press Control Z, A, B, C, C, Control C. Elmo taught me that. Echo this, and then we are on 130 exit code. So, and I think I have 23 as the exit code. So we are not exiting on the right control path. That's the gist. And we're going to change that right now. So the first thing we need to do here is make sure that we do not still have a 0 from the last call, from the last arrow key. If there's escape 41, we have to overwrite the 41, otherwise, and we have to do that before we do the second syscall here. So we're going to move. We're going to use x1 there, so let's move an x1 here and store byte. Is this a byte? Where are we storing this? Yeah, we store a byte w0 in x. Why are we overriding x11 here? That's such a, can we use x12 here, and then we're gonna store this in x11 1. So now well, let's just check it. Hopefully I just overwrote the old arrow key. Well, it's still running. So I think we're fine on the registers. So here now I erase the thing. Now we're gonna do the second syscall. If it's an arrow key, we still get our 40 in the second byte. But if it's not, we get a 0 there. Yeah. So this 0 that we just placed there will be overwritten by an arrow key, but it will not be overwritten by escape. It's if you just have escape. So we're gonna get we had this right here, x11. We get the address back, whatever that is. That's the address of the input key. And now we're gonna get lldb x11 and x11 1, and then compare byte. We could do a 12 here again. Then we can, yeah, compare byte x12 with 0, and if they are equal or not equal, you say continue game. I'm gonna place this here. So as of now, everything, whoa. x12 is w12. Compare byte doesn't exist. So as of now, it's working. Escape is now seg faulting. Okay. So now here, where are we? Here, we should have store byte, no, LDR byte right here. We should have W12. Here we should have in W12 a 0. That means we just pressed escape. And in that case, we're gonna do address page at is alive at page, and register doesn't matter. Change in bird at x1 is alive at page off, and then we're gonna load the we're gonna store, or we're gonna place, let's do x0. I'm gonna move a 0 in x1. Oh my god, I can't type anymore. Don't say I can never type, asshole. x1 0, and then we're gonna store byte w1 at x0, and we're gonna branch to wherever, and right about here. So this should be that. So we can still play. And we get a seg fault. Why do we get a seg fault? lldb x11 is the input key, I assume. LDR x11 fp -8, this should be the input key now. And if we stored, we zeroed it out, we continue the game if the second byte is 0. This is 0, 1, yeah. We have W12. Do I have to step through this? Oh no, this is atrocious to step through. at x0 we move a 0. Is it alive? False. So we're going to store false in x0, which is alive, and then we branch. So this should just end it. The problem is before, actually, right? The sys read 2 bytes, store byte. Yeah, this is a 0 and this is a 1 here. And that works. So now we have the escape key. So we are dying. We can eat. And I can press escape, and we are on the, if I do echo this, we are on the 23, so we are on the correct control path. All right, that is that. Well, there's one more thing, and I do not know if I can do that without notes, because I just solved that yesterday. Let me check the camera. This can be, if you have a better terminal emulator, this can go faster, but we're going to stay within the normal macOS terminal constraints. However, the timing is highly dependent on the implementation. So in other words, if you implement this on the x86 and I implement this on the arm64 and we race each other, the x86 has probably an advantage because it's slower. It's a 77 years old computer. It was 2016, 9 years old now. What? Can this be? I'm distracted. This is okay. Oh, what up? Good morning. Welcome back. Yesterday we had to cut that video a little bit short, and we didn't finish the timing part. So I'm back. We have a little bit of time before the rain starts. Hopefully we get this done. And before we start, I want to show you what actually the issue is with the current timing that we are using. And I set this up here in Premiere, and I tried to line this up. Maybe this is, maybe I include this in the video, but here should be, I don't know which timing I'm using. I think the sleep function. Is it the first one? Let me be clear here. Yes, and you can see if we start up, I lined up the two versions of the x86 and the arm64. On the first frame they move, and if I run this in parallel, you can see that they start okay, but slowly they're getting out of sync. And that's not a real thing if you want to race against each other on two different platforms, so you have to make sure that both versions are in sync, right? I mean, if you take this a little bit too serious. So I had that also, I just don't know where. Somehow this disappeared on me. Is this here? Let me check this here. Yes, this is the version that we are gonna implement now, I think. So let us run it. And here you can see the two versions stay in sync. And they stay in sync. I think I recorded it for 20 minutes, but they should stay in sync for years. Up until the multiplication overflows, which is 18 years or something, or more, I don't remember. I will include that on the GitHub as well. Let me just check if I'm recording properly. I will include that on the GitHub, but I think to race the two versions against each other, we should have a proper timing. So this is what I want to add. and it's a little bit tricky. I tried 2 versions. I'm not even gonna say much about the second version that I implemented. I'm gonna mention it shortly. But the timing I tried yesterday even was not better than the sleep function. So, but as you can see here, if I turn off one version or I turn off the other version, they are, well, this is always over. They are always on top of each other. So they are in sync. So I'm gonna keep my battery life here and stop this abomination of a program. So, what's the task? So so the second version that I tried was timing each frame. So I set a time of day that we implemented at the beginning of each frame, then went before the print function, caught get time of day again. So basically timing this part of the program to this point until we print the playing field, because we have no idea how many instructions and how the instructions are different on the x86 and the arm64 version. So the timing from here to here can vary between 8 and 15 microseconds. That's what I timed it at. And we have a timeout of around 500 microseconds, a little less, but I'm gonna say 500 for simplicity now. And what I did is I said we want to have a timeout of 500 microseconds. We already took 15, subtracted the 15 from the 500, and then gave that to the select syscall, and that implemented or triggered the timeout. Also, keep in mind that the timeout is we print the frame, and then at one point the frame stays in one position. That's the frame, and then it gets cleared, right? With the clear the screen function here. So that's the frame, and there's the beginning of the frame and the end of the frame. And the important point here to get is that the timing we are going to be implementing is for the end of the frame, or not the timing, the calculation that we're gonna do. So when you do this, what I just described, time the frame from the beginning of the loop, and then get another time of day at the print of the frame function, and you get the difference, calculate the difference, you still have a discrepancy between, don't rain on me. You still have the discrepancy that you have to set up the syscalls, do all the calculation after you got time of day the second time, set up the syscall, call the syscall, and then call the screen before you set the new timer. So there is a discrepancy, and that still causes a shift. And the timing I did yesterday was not much better than the sleep function. Before that, I thought it's at least in sync for about 5 minutes. But I will do that again, and maybe I include that in the description or at the end of the video. Okay, so what is the version that we are actually going to use? Well, we know each frame starts with the print function. So let's count that, right? We're going to add, the first thing we're going to do is add a counter and count each frame that we get. And so we're gonna we count each frame, we got a number. So let's assume, for simplicity for the moment, that we start at 0. So the first time we go from here, the game loop, to the first time we call print, we call it the 1. So the moment until we clear the screen should be 500 microseconds. So we have to account how long did we take from the beginning of the loop till we counted to 1, and subtract that from the timeout that we sent to the select syscall. But here's the catch. We don't reset the timer every time. We only do it once before the loop starts. And by doing that, we can calculate how many iterations of the loop were there times 500 microseconds, and then set the timeout accordingly. The advantage here is that in the n+1 frame, we make all the corrections for the nth frame. And we don't get a weird drift, and the snakes will stay in sync. So that's what we're gonna do. It's quite a bit of little things. We have to take care of the microsecond, second stuff. So we do that. But the basic gist now is get the timing once, set the frame count to 0 in the print function, count the frames in the print function, and then time out accordingly to the projection of the frames and the magic number for how long we want to have each frame. 500 I use now. We're gonna use AF00 or A500, I don't remember. It's a number that's just the frame duration. That's what we're gonna use, and after that the x86 version and the arm64 version will be in sync. So let's get that going. The first thing we're gonna do is initialize the timeout. Let me find out where I'm going to do that. Whatever, let's just go up here, clear the screen, raw loop, initialize snake, after the initialization somewhere, print playing field. Let's go to print playing field. I'm gonna do this right here. No, you know where we do this? We do this where the sleep function is. Where's our sleep function? This is the old one, here's the new one. So let's do it under the sleep function because we can need parts of that anyways. Let me check the recording here 1 second. Still good. All right, so let's I have my notes here. So the first thing we're gonna do is initialize the timeout. So what are we even doing? arm64, okay. Initialize timeout.
Yes.
And initialize timeout FPLR. Not gonna forget the bang. Well, this, now we're gonna move the stack pointer and the frame pointer. Our usual stuff, LDP, FPLR, SP, and 16 return. Okay, so we're gonna set the frames to 0, and we should maybe do that first. So I had a little bit of a hiccup here yesterday, so I assume we don't start at that, right? Yeah, okay, so let us go put this for now here, and I named it count frames, not frame counts. Maybe I change that. So the GitHub will be the final version, but this is count frames now, and it will be a quad number, biggest as we can get, and we initialize it to 0. So we go back here, and we need the address. Count frames at page at x0 x0 at page off. So now we have the number, and we're gonna just move in x1 a 0, and just in case we're gonna do in the later stages, if you want to add something like a menu and you want to restart the game, so you have the initialize timeout also resets the frame. Right, so we're gonna store x1 in x0, and that has the frames reset. Now we only have to do the same thing we already did here in the sleep function, or in the, not in the sleep function, in the get time of day function. So let's go to get time of day, copy this part over, and then obviously we need another part where we store it. So let's call this frame start time global, because I like long names.
Oh, you're in an even trickier spot than I realized.
So let's do that. Check in Word. Let's go to the timing, wherever it is. Time of day. Remember, on the arm64, this has to be 64 bits aligned. The stack pointer, this can lead to discrepancies where you don't have, where the syscall doesn't work. So, and here we do not need anything. So let's just do that like so. So now we have the frame start time global, and we're gonna do the end time. Oops, I'm gonna change end here. I'm gonna set this up. So let's go back here. So now we set up the sys time of day call, and now the start will be called once, or it will not be called once because we didn't call it yet. So game loop, we're gonna do this right here. And then maybe I should have checked if everything is still running. Count frames. That's 241. There, 241 right here. That's a comma issue. Everybody knows I don't like that comma, so let's go here. Oh, and we have a long snake. Let's change that back to 4. And that's a long, okay, we are still using the sleep function. So let me check the speed here real fast. Where are we? Right about here, speed adjustment. That's what we called it yesterday. Oh, 6000 A500, I think, is the time I used now. Yeah, and that's a nice moving snake. Just getting caught up, but I want to see if everything's still working. Oh, there's the food. Yeah, and everything's still working. So we are good to go to the crazier parts of the whole thing. Okay, we set the timer, and maybe let's even, where am I? So let's kill that. There is a,
oh wait, yeah, you put me in
we're
check.
here.
Put me in check on moving.
Let me check one thing real fast. There is something which I always forget. Maybe I don't have that. Let me, 1 second here. This is the one. Movew, that's the weird one. So movew minus R. Okay, so because I have it back on 0. Okay, I can close that again. And here we are. That's the one. So let's call object dump on snake. Let's go to the initialize timeout function. run it. Of course, he wants to be asked twice. No. Now we're here. Initialize timeout. Well, first of all, here are our frames. Well, we are just setting up with 0 and it's 0, so it's not very exciting. But here we are, it's 0 and it stays 0. Read a 0. Now here the start global time. Here we have to make sure it's working because of the 64-bit alignment. So we have this, it's 0 and the Syscall goes already started. And here we have the time, the seconds and the microseconds. Loop, start, where is it? No, game loop, that's what we called it. Game loop, so here we're calling it once, and now we are going to calculate with the help of the frame counting. No, we don't do that. We increase the frames now. So let's actually go the print playing field function. And let me check where I did this here, because we want to go out before the rain starts. 1 second. Okay. Screen buffer. So I have this here. I added. So in x86 you have the advantage you can just add in memory. Here we can't do that. So we're gonna do count frames, add page off, and then we're gonna we need the
This part is, you gotta,
oh, okay.
It's like a whole different game.
Yeah, we're gonna there's a number there. We're gonna load the number into x0. We're gonna add or 1 to it, and then we're gonna store x0 in x2 again. So that's all we're gonna do. So now every time the screen gets, or the print function gets called, we count the frames. Beautiful. Okay, then we can come to the main part. Initialize timeout. And initialize timeout. Well, let's run it first.
Actually, no, you can do it.
Still works. And now
Almost perfectly.
a lot of little pieces now that we have to take care of. I want to make sure this goes not out of hand. Initialize. Boom. Oh, this is like, here's so much stuff that I... One moment. Okay. The function is gonna call set timeout for whatever reason. So set timeout is, depending on the frame rate, we're gonna set the timeout or the sleep duration of the frame. I don't know why I call it set timeout. And set timeout and stpfplr. The bang. We're gonna move the frame pointer and the stack pointer. In the frame pointer, we're gonna ldp fplr 16 and return the function. Okay. So let's recap what we need to do. The first thing we need to do is we need the projected time. What's the projected time? The projected time is we have a magic number. We have the magic number is the frame duration in hex. Then we have the frame count. We're gonna multiply the frame count by the magic number. Then we have the number in microseconds. But we need it in seconds and in microseconds. So we need to use our mod function and divide by the maximum amount of microseconds. So 10 to the power of 6. Then we have the duration from the initialized timer to the moment of the frame where we are at now. However, we need to add it to the initialized time to get the total time. Then we're gonna catch the current time. Have say, okay, the frame should end at this time. We are here now. So what's the difference? And then give this difference to the select call. Okay? That's the game plan.
So you're good.
So,
Oh my god.
first of all, let's get everything from memory. And initialize timeout, set timeout. I was here, let me bring it to the top. Let's make it a little bit bigger even. So address page x0 count frames add page. So we're gonna add x0 count frames, add page off. Yeah, so load, we have to count the frames, we get the value, and now we have our magic number. I'm gonna do that not now. We're gonna put this in an EQ, maybe name it, but well, we could do that also now. No, we cannot change it. Move that to 0x. What do I have here? A500. I think I had AF all the time now. 500, and to make it slower for testing, we're gonna have here also a 0x000 LSL 16, so we can make it slower if we want. Okay, so this is the frame count and the frame duration, so we're gonna multiply them now. Move 0, move keep here. Multiply, where do I keep it? In x0, so x0 and x1. So now we have the duration after n frames at the start of the frame. That's an important distinction. Once we have that, we now gonna have to divide it. We have to mod it, divide it and mod it actually. So the total time is 10 to the power of 6, that's microseconds. However, we need that in hex, and that's 4240, F4240. Okay, so I'm gonna just place this here in x1. The 4240, and we need 4. What do I do here? Holy moly. Okay, 1 second. Replace 0. Replace F. LSL 16. So now this is I have this written down here again. Yeah, this is 10 to the power of 6 simply, and this x will be taken care of. But 10 to the power of 6 is 4240, F4240, I'm pretty sure. do I have this here again somewhere? No, okay. So I trust my notes here in the working example more than my write-up in this case, because this is just something I did 2 days ago. Okay, so now we're gonna do some dirty work as well. We're gonna call the modulo function. But as if you remember, we have this now set up in x0. This is the total time in microseconds. This is the microseconds 10 to the power of 6. So we will have in x0 the reminder, but the way we implemented the modulo function, this is now a little bit of dirty work or side effects, wherever we did that.
It's everything from text, so I went to like
Modulo function.
Oh, like the recording function?
Modulo function. Where is it? Here. We are using here the udivide is in x2. So we know the division result will be in x2 the moment we call the function, and we're gonna use that now. Wherever we were. So set timeout is the function, right? So what does that mean? So now that we called it, we know that in x2 is the division, so in x2 has the seconds and x0 has the microseconds, the remaining microseconds. So we're gonna make space here on the stack frame. How much do I need? I set here 32. So let's do 32. And now we're gonna store that. Store x0. Which one? Okay, x2 on the seconds first. fp minus 8. And x0 on minus 16, so we're gonna say here
Let's see something over there. Let's see.
expected seconds passed, and here expected microseconds passed. Now that's the part passed, meaning from the beginning when we timed it based on the frame count, not the total time yet. Okay, but that's fair. So now we take the start time that we timed at the beginning before we started the loop, and gonna add these seconds and microseconds to it. That's the next step. So address page, x0 frame, start time global add page. Let me see if this is correct. Correct. Add page, then we're gonna add x0, add page off. We also check if we are still compiling. We're still compiling. So now we have the time, well, we have the address of the time. But we're gonna need that anyways, so we're gonna store that on the local stack frame as well. So we have the address of the starting frame on the stack frame as well, and now we're gonna load the seconds, the microseconds from both. In other words, these two here, we're gonna get these two from the time and get everything. So LDR in x1, we get x0, 0, that's all the seconds. Then we're gonna get here 8 apart in x2. These are the microseconds. And now we're gonna do, actually we could take, can I do this? We get this, but we're gonna load them. And it's gonna be 3 and 4. So now we have seconds from the beginning, the seconds passed, microseconds from the beginning, microseconds passed. Now we're gonna add them, but they can overflow. So we have to take care of that next. But first we add them. So x1, x1 and x3, and x1 and x3, and x2 and x4. And we're gonna store it in x2 and x4. So now we have added them, but the microseconds can overflow. So we have to take care of that again, and I should not do this here. I'm gonna copy that. I will probably place that on the stack frame, but because of the time constraint, I'm not gonna do that right now. The magic number here, this is just again the 10 to the power of 6. Put this here in, where did I put it? x11. That's I'm gonna make a note here. Oops.
Queen makes it out. Let's go.
It's going to go on the local stack frame. Or on this stack frame. So we have this now, the number. So if we overflow, so if the number is if we have an overflow, we're gonna subtract the microseconds and add a second. So we're gonna simply compare x2 to x11 here to the magic, or the 10 to the power of 6. And if this is less than, we're gonna branch to adjust microseconds overflow. Create our label here. And as I said, we're gonna subtract the second, we're gonna subtract the microsecond from the magic number, and we're gonna add 1 to the seconds. So sub x2, x11, and then add a second to the seconds. These are the projected seconds when the frame shall end after n frames. Like this is we have the
You can't live your guy.
our thief back. You're not. Yeah, this is not for you. This is not go. No. Why are you on me? Are you a programmer? Why are you on my lap? Why is my fly open?
Squirrel's missing. That's too bad.
Yeah. Where are you? Okay. We had an intruder again. Al Capone of New York. Everyone want to say hello? Okay. Back to it. Where were we? Microseconds overflow. We added a second. So, okay, we have the projection. So we have the, let's say you have 780th frame. Then we have the time the 780th frame shall end. That's the time we are calculating. Okay. And if we don't have any overflow, we're gonna just continue here. Yeah, so what remains now is getting the actual time. So we will have this function Actually, up until now, initialize timeout, set timeout. We're not calling it. On my go. Sick. Go. Unbelievable. Yeah. It's chocolate. It's. Okay, so we're gonna use the. Okay, we have the Easter Bunny, we have the intruder. Yeah, whatever. You want the bag now? We have to open it, otherwise we won't have our quiet here. So here, take this. Where are you? Yeah. Take this, and then it's fine. Yeah, it's fine now. Okay, good. Okay. See, that's the Easter spirit. Can we see this? I have it now there. Can I zoom? Okay. Okay. Here is this now. Okay. Back to normal stuff. Wherever we are, whatever we do, set timeout. Let's include the function in the main loop here. So it doesn't do anything yet, but we are at least not crashing. That's always the thing. Are we sure? Like, that seems so unlikely.
Wow, ambitious. I like it.
So let's
And you liked it before.
It's supposed to rain.
let's go here.
Do you like it? Feel the rain on your skin?
Okay, we're back in the game. So let's set the timeout. We have our projected frame and hopefully calculated, probably not. Set timeout.
Ah, Squirrel. You guys don't have squirrels in your team? You guys don't have squirrels in your team?
Slow mo.
The only Texas place I know is down by Union Square.
And I don't like.
No, I do a time lapse.
So set timeout. Man, goodness, I'm like completely like. The squirrel is now the main attraction. So it begged for that egg. Okay, and adjust microseconds overflow. That's where we are. Okay, we're gonna store now from this point on. We're gonna store x1 and x2 again on the frame pointer. So we have now our adjusted and projected seconds and microseconds, and we now put them back on the stack frame pointer. And seconds first and microseconds second here. Is it correct? Yes. So that's that, and now we're gonna get the actual time. So address page x0 frame end time global add page add. Is it in x0? Yes, it is. Page off. And we're gonna store this time now. Do I need that?
Mostly. I mean, I can find it somewhere like anywhere. Although,
I think I need that. And now we need to set up the syscall for the get time of day. So let's go up here and copy this again.
Not to where like I'd be like, oh, I don't want to go there. I can always find something.
Okay, so like what don't you like?
Those people are flabbergasted. I don't like sauces. Or ketchup, mustard, mayo.
Where?
Most of them.
Oh,
I like barbecue, buffalo sauce.
So we have this frame end time. We set the end time. We moved x1 in. We have x1, x2. So now we should get the frame end time in the register. And because that's dependent on the
No one can have it all.
that's dependent on the alignment, we're gonna check that real fast. Like so, set timeout. lldb break set minus address. Run it. Step. I'm gonna advance here fast. Well, let's actually go one time so we can see it. Maybe set timeout. So that's our stack stuff. Register now. Step register read x0. It's exactly one frame. We do our calculation. That's irrelevant. Store x2. Register read x2. That's the microseconds x1. And which one ever it is. Or we're in the modulo function. No, now this is register read x2. That's 0 seconds. Register read x0. That's a500 microseconds. Oh, that's the projected anyway. So that's correct. Frame start time global. Register read x0. Frame start time. Let's see. x64xb. That's the start time. We have this here, register read x1, x3. So this is 1 and 3. So 0 seconds. This shouldn't change. x2 and x4. These are the microseconds. We're now adding them here. Okay. Now we do our comparison. x11 and register read x2. So obviously we're fine.
He has a big dinosaur skeleton.
And now we're gonna store
everything.
register read x1 and register read x2. Step, step, step. And here is now the part that why we're here. We're checking if the syscall fires correctly. 64xb. We are here. And voila. That's fine. We have our syscall firing. So we have the start time and we have the time. Each frame we can time where we actually at. And now we're gonna gauge that against each other and adjust the timeout accordingly. 1 second.
The one where it's like fried, like a good. Or the one where it's like steak sushi, you know, like beef.
Okay. So far so good. We are here. What do we need? Oh, we need the end time. LDR. And now we need, we need the seconds of the, of the current end time. Maybe this is more the current time. I'm gonna change that. End is not end projected frame.
I think we should go. Just see it just
Frame.
pop open my mind.
No, they all.
End time, well, end of the current frame. I might change that name. For now, let's leave it, but yeah, that's what it is. And now we're gonna get the seconds again. LDR x1, x0, 0. And we're gonna get the microseconds, that's 8 apart. And then we're gonna get this part again, our projected adjusted seconds and microseconds.
Pop this minute.
LDR here, and then this is gonna be 3 and 4. Let me check that. Yes. Okay, so now we're gonna subtract the projected time, because that's the one in the future, and to the actual time that we are right now at. Okay, so we're gonna do sub x1, x3, x1. I wrote this here, x3 minus x1, because this is always confusing. And now we're gonna compare that to a 0. Compare x1 to 0. And now one important part here is that we have a branch greater than, not greater equal. Because that's the overflow now can happen if we hit exactly the 0, and we have to, well, what we have to take care of now is that we don't go into the negative numbers and have a large timeout. So we want to have the small correction to our timeout, but not a negative number, and therefore we're going to take care of that. But if we hit the 0 exactly, we will time it out for 10 to the power of 6 microseconds, which is 1 second. And I had that happen on the x86, and there was like all of a sudden the snake would stop for 1 second and then it keeps moving. So that's the greater than at this point. It's a branch greater than, no carry. So let's end no carry. And oh, these are the seconds. No, wait. x1 and x3. No, we're not gonna take care. We're not gonna do. All what I said is true, but we're not gonna do this at all.
Too expensive.
Wait. We are not gonna do that. We're gonna only take. We don't care for seconds. We are timing out microseconds. Seconds are gonna be clamped to 0, so we are not even checking that. I did this here. This is not what we're gonna do. We're just gonna take care of the microseconds. So this is gonna be x4 microsecond, x2, x2. So this is x4 minus, let's write it anyways, x4 minus x2. 2. And then we're gonna compare that to 0. So everything I said is correct, it's just not for seconds, we're gonna do it for microseconds. And then branch to greater than, no carry. So no carry. And here we're gonna set up the Syscall now. But if we have to, I think we have 32. We have 32 free. Let me get the number again.
I don't mind what I do, but I hate my boss.
So let's get the magic number, and I'm gonna put this most likely on 32 stack frame in a second here. But for now, let's add x0 to x11. So meaning we are in the negatives, and we're gonna take the 10 to the power of 6 to shift it back into the positive numbers.
Everything
Yeah, so if we are here under 0, we are gonna, so if we are greater, then we're gonna do no carry. If we are at the right stage. But if we are in this code block, we are under, we're in the negative, so we're gonna shift it back. Okay, so, and now the only thing that remains is we have the projected end of the frame and we have the current time. So now we're gonna take the difference, we already took the difference, now we're gonna set up the select frame count. So, address page, why did I choose 23?
Got it.
Okay, so just, oh, I do not, what did we call this? 1 second, I think it's in this, 1 second, not too, let's go as fast as possible, but not faster, right? Let's mark this, let's go to the sleep function, to the new one, speed adjustment, that's what we called the time here. So we're gonna have to take this here as well, page, add x23, speed adjustment at page off, and now move in x24 0. Okay, yeah. So now what we have to do is we have to call the select and we have to have the correct timing in the speed adjustment struct. So we're gonna store that right now. I don't know why I have here 24. I'm gonna probably take 0, and x0 is taken. So x23 0, that's the seconds. We are clamping them to 0, and x0 has the, I have something in my eye. It has the projected microseconds, so we're gonna place them at an offset of 8. So this is here just the clamping. Maybe we do this like this, because we're never gonna time out more than a second. The second is always 0. And the microseconds are important. And they should, now that we took care of the greater than, they should never be a second. They should always be greater, so whatever, between something and 500 microseconds, or the whatever it is, A500. Okay, let's copy the Syscall, because I think we are almost here in the rain. So let's be, do we need to still, we're gonna copy all of that, even though I think we just did that. Let's go back here. X4 is x23 should still be in x4. So okay, I think we can do 2 adjustments there. Let's go. And now it goes slow. That's a good sign, because we still have the sleep function. And now it's running. And I think we're gonna test this now with our magic number, set timeout, so we are sure we are really here. Now it should be pretty slow or fast, at least the change. Why is it fast? Oh, because, no, keep 0. Let's take an F here. Okay, that's slower. So maybe we can't do that for the select call. So that's slower. Can go down to 8 or something, maybe 9. I think that's when the terminal gives up on us. And yeah, that's still fine. It's a little chunky, but we're good. So now the two snakes should be equal. Well, let me get this back to something I'm familiar with here. And let's check it. And we can still kill each other. We can still kill it. So let's go down here. We have 32. So let's store x1 str x1 on fp minus 32. Right, and we can do that right here. Load this in x11, so this should be fine. And we use the magic number again where?
Joseph,
right
come
about
get your bike.
here.
It's supposed to start raining now. Come on.
It's supposed to start raining
How am
now.
I going to take the stroller down?
So
Joseph, come on.
let's place this here. Let's test it. It's still working. Let me get the magic number again here. I just want to make sure everything is really working. Yes. Undo it again, so we have this adjustment here, and we had this adjustment here. And now the last thing is, I think we can place this here directly in x4, and then we can time out this. So if this doesn't work, yep, that's fine. So this is gonna get rid of this, and now 4 we can use 5 here to be a little bit cleaner. All right, and that's the timeout in sync with the x86 version. So in theory, it doesn't matter if you're on the x86 version or the arm64 version, we can now race against each other and it will be fair. Obviously this concludes the Easter special. This was all I set out to do, and the squirrel made me open the package, so we might as well kill the last bunny so I get this also out of my chest. Happy Easter, and that's the end of the Easter special. We might do a bonus because racing each other is not really fun if you don't have a score. So we're gonna add a scoreboard. I'm gonna show you real fast how this is going to look. Snake. This is going to be something like this. So we have a scoreboard. And then the timing is correct, the score is correct, and then we can set up, we can see who's better. I'm just kidding. But yeah, so that was all we set out to do. I think this is also the main part of the code. This has everything that we needed to have. Happy Easter once again on May the 4th. So that's it. I don't know when I have time to do the scoreboard, but I think I'll try to do it soon. Thank you very much for watching, and see you in the next one.